this talk is going to be about finite-dimensional algebras mostly, and so all algebras in the talk are going to be given by as path algebras of equivalent relations, and then we're going to work over algebraic closed fields. So please algebraically closed. And then, so what is a path algebra of equivalent relations? So we have an oriented graph. And then one can consider as a vector space the algebra given by paths in this graph. So we have some paths of length 0, and then for this algebra you have all detail. So the algebras are going to be given like that, modulo some relations, and yeah, that is the setting. So let me start by defining what the graph algebra is, and it will be going to be given as a path algebra of equivalent relations, as I said. So the input data to define a graph algebra is going to be graph, gamma, which is a written graph. So this is a graph with a cyclic orientation of edges around each vertex. And this is going to be a finite graph and a multiplicity function m from the set of vertices of gamma to natural numbers. So let's have some examples. So this is a graph, and when I draw something on the board, I'm assuming that the edges are oriented in a counterclockwise order. So to this data, I want to associate a quiver with relations. So to get a quiver, I need vertices and arrows, and vertices of the quiver are going to correspond to edges of gamma, and then arrows are going to be coming from this cyclic order. So we get something like that. So vertices of the gamma correspond to edges of gamma, and arrows correspond to the cyclic order. Okay, now what about the idea of relations? Well, one can notice that the arrows of this quiver that we just constructed can be divided into these cycles going around the vertices. And then there are two types of relations. So first we have that, okay, I said counterclockwise and clockwise, so now the orientation is clockwise, sorry. Anyway, so the first type of relation is that when we go from one cycle to another, then we get 0. And then the second type of relation is going to involve this multiplicity function here, which was another input data, and the relations are going to be given. So for each edge, we have two vertices to which this edge is adjacent to, and then the relations are that going around one cycle, the correct number of times is going to be equal to going around the other the correct number of times. So we have V, W, and then we have one cycle. So the multiplicity of 3 times, and this is going to be equal to and then a Brauer algebra, the gamma, is just going to be the path algebra of this quiver to gamma with relations given by these two types of relations. This is a finite dimensional algebra. So these algebras first appeared in representation theory as blocks with cyclic or dihedral defect group, and they are very well understood. So there is a classification of finite dimensional and decomposable modules over such algebras, and a lot of things are known about the module category, but we are going to be interested in the equivalences of derived categories.
Can you just draw Q gamma separately for that example?
Yes. So this was the gamma. And this is that better?
Yeah, okay.
Okay. And maybe if you want another example, let's just look at one edge with two multiplicities m and n, and then the quiver will have two loops, and so this is going to be here xy modulo. So going from one cycle to the other is 0. So xy is equal to 0 is equal to yx. And then if these are the multiplicities, then x to the m is going to be equal to y to the m. Yeah. Okay.
One question.
Yeah.
In modular representation theory, do the fields typically has finite characteristic? That's right. And can it then also be algebraically closed, or is the case that which appears there typically not algebraically closed?
I guess you can consider both. Yeah. I don't know. What do the experts say?
Yeah, you want to consider both, yeah.
Okay.
You can take algebraic closure, yeah? Okay.
Yeah. So what about derived equivalences? Well, the first question one can ask is...
So in terms of, since you're on the topic of motivation, so what do you expect to read? It's over, but I want to make it a little longer. So what you read about the ribbon graph on this Brauer algebra, what kind type of, what is the reason to look at this Brauer algebra when you want to study the ribbon graph? Or you said in representation theory,
So this is just some combinatorial way to define an algebra, and so we are not studying ribbon graphs. I mean, we are and we are not. So we're studying the algebras, and they're just given by this data. But then the graph governs very much the behavior of the algebra.
But I mean, you did not. I mean, I don't imagine that someone woke up a morning and said, "Oh, I'm going to define an algebra this way," right? So that's the reason, the multiplicity thing and those things. They should have a.
Yeah, I guess for trees, these are coming from some Brauer characters or something. But then also in representation theory, one can consider special biserial algebras, and then they are defined by quivers such that we have at most two incoming arrows and at most two outgoing arrows. And such quivers behave very nicely because one can determine the more or less Alexandra-Zvonareva quivers because of that. And then if you additionally assume that the algebra is symmetric, so in terms of the derived category, this says that the perf is 0-Calabi-Yau or something like that, or that you have a symmetric form, then one naturally can construct this graph from that. Yeah. And this is a theory. Okay, more questions? Okay. So, yeah, derived equivalences. The first question one can ask is whether this class is closed under derived equivalences, and the answer to this is yes. So this is the first theorem by Antigraph and myself. If we have that A is a Brauer graph algebra, and B is some other algebra such that their bounded derived categories are equivalent as finite categories, then B will be also Morita equivalent to Brauer. So if it's basic, then it will be as an So A, this is also algebra, then B is Morita equivalent to Brauer algebra. Okay. So now we are interested in equivalences inside of this class, since we know that there are no equivalences going out of the class. And in order to study them, I'm going to introduce some higher structures, and in order to relate myself to the topic of the conference. And the higher structures are going to be infinity categories. Okay. So let's briefly recall what an infinity category is. So, infinity categories. So, A. For that, we are going to have a set of objects. A. Set of objects. And then to every pair of objects, we have the space of morphism, which is going to be a Z-graded vector space. So and then instead of just one composition, we are going to have infinitely many operations. So if we move from So from any n greater or equal than 1, this is going to be a linear map of all the 2 minus n. And then in addition to all this operation, we are going to have a infinity constraints. So I'm not going to write out the signs, but basically if we have something like a series of composable maps, then we have equal to 0. So we take a sum with some signs. For always, so we fix a tuple of length n, and then we consider always that we can put this 2 type of brackets, one inside and one outside. We sum them with appropriate signs, and this is going to be 0. And for example, this means that if we have only one entry, then there's the only way to do that is to get u1 squared, and this says that this created vector space is the complex. Okay, so these are the infinity categories, and for me they are going to usually be coming in the form of quivers with relations again. So the objects are going to be vertices of the quiver, and then the bases of the home sets are going to be given by arrows and paths. Okay, what else do I want to say? So now the goal is to define some infinity category analog of Brauer algebras and to study them. And what will be the relation with the derived equivalences? This is going to be coming from the category of twisted complexes. So what's that? So if we have an A infinity category A, then we can define another infinity category, the category of twisted complexes, and the objects of this new category are going to be given by pairs x delta, such that x is a formal direct sum of formal shifts of objects of A. And this is going to be a lower triangular matrix. So one can think of something. So here we have x. So if you have a DG algebra or just an ordinary algebra, one can consider complexes of modules. So we have x0, x1, differential, something like that. And then one can informally think of that as we take the object of 0, x1 shifted by -1, and then the differential is given by this lower triangular matrix. Okay. So these are the objects, and then on these objects one can also define the graded vector spaces of morphism and the infinity structure. I'm not going to talk about that, but anyway, this is again an A-infinity category. And to this A-infinity category one can associate its zero homology category. So here we just take the same objects, and the morphisms are going to be the zeroth homology groups with respect to this differential coming from the infinity structure. And this is always triangulated. Okay, and now if we were starting from an algebra A, and we can consider the category of finite dimensional projective modules over A. A has a finite dimensional algebra. And then the homotopy of the zero twisted complexes of this category is just going to be equivalent to the compact objects in the derived category of A. And then if we want to study derived equivalences of the bounded derived category, of the unbounded derived category, we can instead study the equivalences of the compact objects, and this is the same as studying equivalences of this category here. Okay. So, questions about that?
Yeah, sorry. So here, right, your A here is just an abelian category to start with, is it? Or
Which one?
yeah. So you're defining twisted A.
This was an infinity category.
So okay. So A is A infinity in the first place. Okay.
Yes.
And then, but then the twisted things are A infinity as well.
Yes. Yes. And so you can consider A naturally inside of the twisted complexes.
Okay.
As things without shifts and sums.
Okay.
Okay, so now I want to define some A-infinity analogues of Brauer algebras, and for that I will need the connection to dental algebras and to partially wrapped Foucault categories. And in order to do that, I will first define the surface corresponding to a Brauer graph. So as before, we have some ribbon graph gamma, and this was fixing us a cyclic order of vertices, of edges around vertices, and any such ribbon graph can be embedded into a minimal surface in the following way. So you just take a ribbon and you start gluing it along the edges, and then the cyclic ordering tells you how to continue when you reach a vertex, and so on. And so this is minimal in the sense that if we cut the surface along gamma, then this will be a union of analog with one boundary component inside. So gamma can be embedded into a unique minimal surface. And this is going to be called as gamma. Okay, so now the connection with dental algebras. So I'm not going to define what they are, but they are all going to be constructed from Brauer graph algebra, so you can take this as a definition. So now if we have a Brauer graph algebra, for example, the algebra associated to this graph here, so we have the surface, and then in each cycle of the Brauer graph algebra, we can fix one error. So we can fix an error in each cycle, for example, in the following way. And then we can form the ideal generated by these errors, and we can take the quotient of the Brauer graph algebra. And so J ideal of relation generated by one error of each cycle of the gamma. And then on the level of the surfaces, this corresponds to cutting these errors and dragging the vertices, the boundary of the surface. So the result is going to look in the following way. So we are dragging this vertex here, this here, and this here. So the graph is going to look like that. And then the errors which survived, modding out this ideal relation, is going to be like that. And this is a gentle algebra. And then to go back from this gentle algebra to the Brauer graph algebra, one takes the trivial extension. So in this direction we have cut. So this is B gamma, and this is A, and then the gamma is isomorphic to the trivial extension A. And this is a result of strong. So what is a trivial extension? So this is as a vector space. This is A direct sum with the dual of A. And then if dual with respect to the field K. And then if we have two elements, AF and BG, then their multiplication is given by AB. AG plus F. So here we use the bimodule structure and the dual bimodule in order to define this multiplication. So any gentle algebra arises in this way, and then any Brauer algebra is a trivial extension of a gentle.
A question, do you have an assumption on the multiplicities, or is this for arbitrary multiplicity?
This is for multiplicity 1. Thanks a lot. Yes. Yeah, thank you. Okay. So now for this gentle algebra, there is a version of A-infinity categories which are coming from partially wrapped Fourier categories, which allow to study their derived equivalences. So let me tell you about that. And this is going to be, so I'm mostly following Haydn, Kazakov, Kansevich. And this is also based on Aru and Bogland. Okay. So for that, we can fix sigma to be a smooth connected compact oriented surface with boundary. And we are going to fix the set of marked points on the boundary of sigma. And we're assuming that this set is not empty. And then also we are going to fix a line field. So this is a section of the vectorized tangent bundle of sigma. So we have the surface, and at each point of the surface we're fixing a line such that this value is continuous independent point. Okay, and this line field is going to allow us to equip the home spaces with some grading. Okay, now we are also going to consider the full system of graded arcs. So these are arcs which are going to go from one marked point to another marked point, and they're not going to have intersection in the interior of the surface. So the surface will look something like that. And then the fact that this is full means that the arcs cut the surface into polygons and analyze with one boundary component inside of each one of them, and without marked points. The fact that it's graded is saying that we fix a homotopy between, so if we have a curve, then at the point of the surface we have the line field, and we also have the derivative of the curve, and we're fixing a homotopy between them. Okay, so this is the setting, and one can think about that exactly in these terms. So the arcs are going to give us vertices of some quiver, and then the intersections between the arcs are going to give us morphisms. So this is a partially wrapped Fourier category of sigma. So objects of the arcs of A, then basis of morphisms are given by graded intersections, and the grading of the intersection comes from the grading of the curves. And then we have composition. So if we have an intersection like that, this gives us some morphism here, and then another intersection gives us another morphism, and then their composition is this intersection if this intersection exists, or if this was something like that, then this composition would be 0, because there is no intersection corresponding to it. Okay, so this is the composition. Then the differential is going to be 0. And then the higher operations are going to be coming from immersed disks. So if we have an immersed disk such that the edges are the elements of the system of the arcs, so this belongs to A. And then we have this intersection corresponding to the vertices. So the disk gives us a sequence of composable maps, and then the higher operations are going to be something like E, A1, AN, and this is and then there's another expression of the same form where B is now on the first place for this. Why is this nice for us? This type of infinity relation tells us that if we have just a disk like that, then here we have an object which can be denoted by gamma 0, and we have that mu of AN, A1 is the identity on gamma 0, and this gives us some isomorphism in the A0 twisted complexes between the object corresponding to gamma 0 and the consecutive cone of all other arcs. In particular, this means that we can add and remove arcs as we want without changing this category, and this means that the subcategory they generate inside it are the same. And so this means that this category doesn't depend on the arc collection at all, because for any arc collection we can complete to a triangulation and then flip the triangulations. So we get that 0 twisted complexes of A depends only on the surface, the marked line, and the line here. Okay. So now we can go back to our graph algebras, and we want to do the same as the trivial extension here, but now for this infinity categories. Any questions about Fokai categories I can't answer?
Just to clarify, right, so you've got a system of arcs. So the arcs are going between the marked points, is that
Yes.
right? And the arcs give you objects of the Fokai category.
Yes.
And you've got a morphism between two arcs for each intersection point.
Yes.
And you say graded. What's the graded to do?
So the arcs were graded, so we were fixing some homotopy between the line field and the derivative of the arc.
Right.
And then two arcs are graded, and this gives us a lot of different things. And basically, if you look at pi1 of a point next to the intersection, this is the projective line, so this is a circle, so pi1 is that. And then you can cook up a class there for the intersection, and this gives you a number.
Okay.
And this is the grading on the home spaces.
Okay.
Okay. So, now there is an operation of n-infinity trivial extension. So basically, in the same way as it is defined for ordinary algebras, we can take the same objects as in the initial infinity category, and then for each pair of objects, we can consider the following Hom space. And also we can shift this by n, and this will be, on that one can define the structure of an infinity category. So one, there is a way, and then this A infinity Brauer graph categories are one, the multiplicities are all one, they are going to be the same with the trivial extensions of partially wrapped for color categories. So what do we do for that? For that, now we need to take a surface with a line field and a set of punctures in the interior of the surface, and this corresponds to this operation where you drag the punctures to the inside. And maybe it's not so hard to understand here why this has to do something with the trivial extension. So basically, if we have something like that, then we just have one dimensional Hom space here, and when we go to the trivial extension, for this arrow, we have the dual arrow which goes back, and then for each idempotent, we also have a dual map, and they turn out to be the same. So that's basically the idea. So now, what do? We fix a smooth connected, compact oriented surface with a non-empty boundary as before. Compact oriented surface with non-empty boundary, but now we fix a set of marked points in the interior. And also the line field is going to be defined on the surface minus the set of the marked points. So this goes from, we throw out the marked points with the projectivized tangent. So this is the line field. And also we need to fix the multiplicity function, now going from the set of punctures to natural numbers. Okay, and then we want the same sort of relations to hold as before, and for that one needs to require that this the line field and the multiplicity function are compatible. So additionally, we ask that, so let me write this and then explain. So for any loop on the surface, we can compute its winding number with respect to the line field. And this is just going along a curve, the loop, and counting the number of intersections the derivative makes with the line field, the signs. And then if we have a puncture, we can consider a loop going around this puncture, and this will give us a winding number of the puncture. And then we ask that the winding number of the puncture times the multiplicity of the puncture, all these are some equal number for all punctures. And basically the reason for that is that this winding number of the puncture will be the degree of the morphism when you compose all the morphisms going around the puncture. And if we want the relations to be homogeneous, one needs to fix that. Okay. So to this data, one can define the infinity category in a very similar way like for the Foucault category. So we are going to have sigma plus additional higher operations, and this higher so these additional higher operations are also going to come from disks, and they all look in the following way. So we have a sequence of composable morphisms. Now the punctures are in the interior of the surface, so we can go out of the disk, then we can come back, and the result of the higher mu applied to the sequence of maps is going to be this. And this is related to the fact that when we compute the trivial extension, one of these maps here is going to be coming from a functional, and this is also going to be coming from the functional, and this is how this infinity trivial extension works. Okay, this is and we can define that, and in case one is isomorphic to the trivial extension of this spatially wrapped Foucault category, where we drag the punctures to the boundaries of sigma. And so this we use to construct the infinity structure in case when the multiplicities are 1, and in case when we have high multiplicities, we consider some branched covering of the surface and some group action by the deck transformation group, and using that one can define these infinity categories for high multiplicities. But I'm not going to talk about that. But so what's the point in all of that? The point is that this argument here still holds. So here was also the arc collection, which is full. So it cuts the surface into polygons and amyloid, and there's additional technical condition that all punctures have access to the boundary. So here, from each puncture, we have a path to the boundary component such that this path doesn't cross any of the arc collections. So this is the technical condition under which one can interpret this as this trivial extension. Anyway, one can define these categories, and one can still add and remove arcs. when one creates disks. So one can get some theorems. So this A, A0 of twisted complexes of A depends only on the surface, the line field, the functors, the line fields, and the multi-set of values of the multiplicities. And then, for example, if one restricts to the case where all the degrees of the errors are 0, so the case of the ordinary Brauer algebra, then one following this path, one can actually obtain a complete derived equivalence classification of Brauer algebras. So this is for ordinary. And this was done in the joint work with Opper. But I'm not going to talk about that further, so now I want to indicate that there is an action of some braid group on the derived category, and for that I will need to define spherical twists. Any questions about that part?
So let me ask if I understood this correctly. So you're saying you can, if you have a Brauer graph algebra, you can show that it's equivalent to some A infinity category which is intrinsic to the surface, and thus you now know that it is intrinsically equivalent to some object from the surface, and thus any two Brauer graph algebras which come from the same surface are equivalent if and only if there's the same surface. And that's how the classification.
More or less, yes. Okay. And then you have the action of the mapping class group, and you, using work of Lippmann and Hausdorff, the orbits of the mapping class interaction is defined, and one can interpret the invariance of these orbits using some non-invariance of Brauer graph algebras. But this is only for degree 0 errors. Because the invariants were not studied for other cases, basically. So what are spherical twists? These are some special kinds of auto-equivalences which come from spherical objects, and they were defined by Seidel and Thomas. Spherical twists. So what do we need for that? So we fix some triangulated category T over field, and it has a fixed. We assume that it has a fixed. Also, we can fix some number n and z, And then we can define what a spherical object is as. A spherical object if the following set of conditions follows. So basically, the idea is that it has a homology of a sphere, but we also need some finiteness condition and some Calabi-Yau condition with respect to S. So first, we have that the dimension over K of the total great Hom space from X to S shifted by K is finite for any X in T, and this I will denote by XS. Then symmetrically, the dimension of the same thing, where we exchange X and S, also has to be finite for any object in the category. So this is the first condition. Then the second condition is that thing I mentioned about the sphere. So this is two-dimensional, and T is in degree n. So this is an isomorphism of algebras. And the last condition is that the Calabi-Yau condition. So we have a composition of the following form. X n minus j, and this goes to Hom from S to S shifted by n, and then when this degree is 0, we wanted to go to something to T and not to the bigger part, so we find out what is spanned by the identity on S. So this is only for n equals 0, and this is supposed to induce a non-degenerate pairing. Okay. So this is the definition of a spherical object, and from that one can construct an outer equivalence, which is a spherical twist. So this is just cone of Hom from S to X with S to X. So this is computed using the equivalence. And this is an outer equivalence of T. And then if we have two such objects, then if there are no Homs between S1 and S2, then this commute, and if there's a one-dimensional Hom, then the outer equivalence satisfy the braid relation and so on. So this were studied quite a lot to study the action of the braid groups on various triangulated categories. And I'm out of time. But so another theorem I wanted to indicate is that when all the multiplicities are 1, then basically the projective modules over Brauer graph algebras are spherical objects. So this derived category, or the category of perfect complexes over Brauer graph algebra, is the natural place to study spherical twists. And then in the group of outer equivalences of this, say, H0 of twisted complexes of a Brauer graph category, one can consider the subgroup generated by spherical twists with respect to the objects which are not loops. And this subgroup will be isomorphic to the subgroup of the mapping class group generated by half twists with respect to either all simple arcs or a particular fixed system of simple arcs, because this is the same. So let me write that. So the subgroup equivalences of zero of nested complexes A generated by lists of objects corresponding to the curves, which are not groups, is isomorphic to the braid twist group. So these are some subgroup of the mapping class group generated by, so we have an arc on the surface, you can put around it a small neighborhood, and then you can somehow put a fork inside and twist it, and this will be a half twist, and this gives the diffeomorphism of the surface, and this will be the same. Sorry for going over time.